For new electricity generation, solar and onshore wind are now the cheapest bulk energy sources on the planet. We measure that cost using the levelized cost of electricity, or LCOE. But LCOE has a structural blind spot. It strictly calculates plant-level generation costs, assuming every megawatt-hour produced holds the exact same commercial value, regardless of what time of day it enters the grid. On a grid heavily saturated with solar, the simultaneous spike in generation during midday hours creates an extreme oversupply. In markets like Germany or California, this drives wholesale electricity prices to drop to zero or even go negative. This forces a rapid decline in the project's capture rate, the actual revenue earned per megawatt hour. Then the sun sets. Demand spikes exactly as generation falls away. The raw volume of energy a plant produced at noon is irrelevant if it cannot deliver power when the grid actually needs it. Because LCOE ignores the time value of electricity, optimizing a plant purely to generate the cheapest raw volume is an outdated strategy. That strategy is completely incompatible with the requirements of the grid's fastest-growing consumers: data centers, AI computational hubs, and advanced manufacturing. These off-takers demand absolute certainty. They have near-zero tolerance for disruption. Their commercial standard is a flat, unyielding 24/7 power supply, not an annualized average of intermittent generation. The engineering challenge is clear. We have to quantify the cost of transforming a variable, weather-dependent resource into a continuous energy block. To solve this, the International Renewable Energy Agency developed a new metric, the Firm Levelized Cost of Electricity, or FIRM LCOE. This measures the specific project-level cost required to guarantee a highly targeted reliability threshold. Delivering firm power requires precise techno-economic optimization between energy generation and energy storage. Attempting to force that certainty using batteries alone is a mathematically guaranteed way to bankrupt a project. Let's build the firm LCOE equation. We start with a solar plant's daytime generation curve. Overlaying a continuous demand block exposes severe nighttime gaps. First, batteries absorb excess midday generation to fill evening deficits. Then, we introduce generation overbuild, expanding the solar array to cover all remaining hours. This gives us our formula. The firm LCOE equals the base generation cost plus a firming premium, the exact capital expenditure of the required batteries, and the overbuilt capacity needed to flatten the curve. We can test this premium in a real-world model. We'll use a hypothetical 100-megawatt solar plant in Las Vegas, Nevada, with a $43 base LCOE. This chart graphs pushing reliability to 100%. The blue curve tracks the cost using only batteries. Up to 84%, minimal storage keeps firm LCOE under $80. But passing 85%, the economics break. The cost violently spikes vertically off the chart. This threshold is known as the battery wall. It is the exact mathematical point where the marginal cost of buying enough storage for the next percentage point of reliability becomes financially catastrophic. The physical reality driving that spike is multi-day low-generation weather events, known as the Dunkelflaute. These are periods where solar irradiance drops sharply for consecutive days. To bridge a 4-day weather deficit with batteries alone, developers must purchase massive storage capacity. But that deep reserve will sit idle for 95% of the year, destroying the project's economics. The solution is a counterintuitive approach. Returning to the Las Vegas data, look at the brown curve, representing intentionally overbuilt solar capacity. The result is immediate. Pairing storage with an overbuilt array achieves 95% reliability for just $113 per megawatt hour, completely bypassing the battery wall. Intentionally building extra solar panels and actively throwing away excess power on sunny days is mathematically cheaper than constructing deep-duration chemical storage. There is one final lever to compress these costs further: portfolio diversification. We can hybridize the site by deploying solar and onshore wind together. Wind and solar possess natural meteorological complementarity. They reliably produce power at inverse times of the day and opposite seasons of the year. When you pair them, you physically shrink the duration and depth of your supply gaps. This chart compares generation models at a high-quality wind site. The gray columns represent firming the wind asset alone, while orange represents a hybridized wind plus solar system. At the 95% reliability tier, integrating a complementary solar component drops the firm power cost from $95 down to $60 per megawatt-hour. The cheapest path to continuous clean energy is almost never a standalone asset. It requires deliberately pairing inverse generation profiles to share a localized battery reserve. Taking these project-level optimizations and applying them globally reveals a rapid macroeconomic shift over the last decade. The catalysts are steep hardware discounts. Since 2010, solar PV costs declined 87%, and lithium-ion batteries collapsed by 93%. This line chart tracks firm 95% reliable solar plus storage across 7 markets from 2020 to 2035. In regions like China, firm solar already delivers below $50 per megawatt-hour. Premium sites in India, Brazil, and Australia will cross below the $60 mark by 2035. Geography dictates destiny. Regions that naturally experience the lowest instances of multi-day weather lulls hold a permanent structural economic advantage in generating continuous clean power. We can measure the true weight of these numbers by comparing them directly to the traditional heavyweights of continuous reliability: combined cycle gas and coal-fired plants. A new fossil fuel generation plant typically produces electricity at between $70 and well over $100 per megawatt-hour. In prime resource zones, new highly reliable firm hybrid renewables are now structurally cheaper to operate. Beyond the raw price, these systems hold critical commercial advantages. A firm hybrid plant can be deployed in under 2 years, and once built, it is permanently insulated from global commodity fuel shocks. Competing purely on the lowest base generation cost is no longer the objective for power grids. The defining bottleneck of the energy transition is integration. The market will favor developers who execute the complex calculus of generation overbuild, localized storage, and physical hybridization to deliver absolute grid certainty.